The purpose of this video is to visualize two very important concepts in modeling, bias and precision. And to do this, we're going to take a step back and look at the modeling process from a greater distance. So whenever we're building a model, we always have some target population in mind, some population that we care about. And in this case, we're using the NHANES data. The target population that we care about is the non-institutionalized US population. But what we can actually see is only a small sample of that population that we care about. And so the population we care about, we call the target population, and the population that we can actually see is our sample. So the sample here would be the people who are actually in your data set. So what we would like to be able to do would be to find the structural relationships between the variables in the target population. That's the model. That's a structural part of the model that is generating the data. But what we can actually estimate is the structural part of the model for the sample. And so bias and precision is related to how the structural part of the sample relates to the structural part of the target population. So what I'm going to do here is I'm going to create a simulation. And what I'm going to do is I'm going to create a data set for a target population. And since I'm creating the data set, I will choose actually the structural part of the model that is generating the data for the target population. And the model I'm going to choose will be y equals 2 plus 5x1 minus 5x2 plus a random portion, which is going to have a mean of 0 and a normal distribution. And so this function is actually going to be the structural part of the target population. And I'm going to generate data points around that structural part, which will have this function up here. And then what I'm going to do after that is I'm going to take random samples of the individuals in this target population and then use the actual method that we use, which is for a continuous outcome, is least squares estimation. I'm going to use least squares estimation to estimate the model up here in the sample. I'll estimate the structural part using least squares estimation, and we will see how the model that we have up here in the sample relates to the true structural portion of the data in the target population. So I'm going to choose, starting out here, I'm going to create a target population that has an N of 2,500. And then let's start out with a small sample and see what happens. Let's take samples of 10 people. And so we're just going to take 10 people randomly out of 2,500. We know the structure of the model, of the data generating structure in the 2,500 people, our target population, and we're going to take 10 people randomly and then use least squares estimation to estimate the structural portion of the target population within the sample. Let's see how close these are to each other. So let's first take a look at the structural part of the data generating process in the target population. So this is a picture of the structural part, which is y equals 2 plus 5x1 minus 5x2. So you can see that the value of y is increasing as x1 increases, but the value of y is decreasing as the value of x2 increases. Now the next thing I want to do is I want to generate 2,500 data points. And I'm going to generate them by first using the structural part of the data generating process. I'm going to place a random number generator at each point, and then I'm going to allow it to generate one data point, and all of the data points that it generates will have a mean of 0 and a normal distribution. So here we can see the data points, and if we add the random portion using a red line, we can see all the random portion of the data generating process. That's the red. The blue is the structural portion. The red is the random portion. And if we were to look at a histogram of all of these red lines, we would see that they have a normal distribution with a mean of 0. So some of the data points are above the structural portion. Those are the positive data points that were generated by the random number generator. And some of them are below the structural portion. Those are the negative numbers that were generated by the random number generator. Now, what I'm going to do next is I'm going to, out of these 2,500 points, and these points represent an individual. Each of these points represents an x1 value, an x2 value, and a y value. And I'm going to randomly select 10 of them. And then using those 10 data points, I'm going to use least squares estimation to estimate a linear regression model for those 10 data points. And the way that I'm going to do it is using the normal process, which is to minimize the squares of the distances between the data points and the structural portion of the model. So the statistics program is going to do that work for me. It's going to orient the structural portion of the model in such a way that it minimizes the squares of the distances between each data point and the structural portion of the model. So let's try one. And starting out, why don't we just get rid of all of the data points and their random components? Let's just keep the blue structural portion of the target population here, and then we will be able to see how closely the structural portion of the model in our sample of 10 individuals matches what we're actually trying to see, which is this blue structural portion of the data generating process in the underlying target population. So let's draw 10 random samples and create a linear regression model for those 10 samples. So here we have one, and some of the data points we can't see because they're hidden below the regression model. But there are 10 data points here, and we can see that the model that is estimated by least squares estimation for the 10 people that we randomly selected from the target population of 2,500, it doesn't actually match very well. They're actually quite different from each other. And remember, the orientation of this pink plane, which is the regression model estimated by least squares estimation for these 10 individuals, that is going to determine the beta 0, the beta 1, and the beta 2 in our model. And for example, if our exposure variable was x1 and x2 was our conditioning variable, the beta coefficient that we would really care about would be the beta coefficient for x1, the beta 1, because that would be the estimation of the magnitude of the association between our exposure variable x1 and our outcome variable y. That's our cause and our effect. And remember, we said that if we see a kind of angled relationship between them, the structural portion of our model has an angle, that tells us that there is an association between exposure and outcome, cause and effect, and then we can begin to link that with our ideas about the causal structures of reality that we encoded in our DAG, and we can make statements about the causal structure of reality. So the magnitude of that beta 1, which is a coefficient for our exposure variable, matters a lot, and it's determined by the pink line. What we really want to know is, what's the beta 1 in the target population? And you can see here that it actually has the wrong sign. In the target population, the blue structural portion, the beta 1 is positive. As x1 increases in the target population, y is increasing. Here in our estimated model, as x1 increases, y is decreasing. So there's quite a bit of difference between what we're trying to see, which is the blue one, and what we can actually see, which is the regression model in our sample. Now, one of the reasons that these are so different is because I drew a very small sample. So let's just look at it for a while, and let's look at what it looks like if we were to repeatedly sample from the population. So I'm going to take these 10 data points, I'm going to put them back into the target population, and I'm going to randomly select a new 10 points. And let's just do that again and again and sort of watch how the estimation procedure performs in repeated samples in the target population. So what you can see is that there's a lot of variability. And some of the samples are actually very close to the target population, and some are quite different. Now, the thing to recognize here is that when you are looking at the NHANES data, you are looking at one of these pink planes. You have a single sample of the US population, and you are estimating a regression model in a single sample. Now, do you have a sample that gives you a regression model that is close to what's true in the target population, or do you have one that gives you a regression model that is quite distant from the target population? Well, you'll never know that. And so what we have to think about when we are modeling is we don't think about what is happening in our particular sample. What we're thinking about is what would happen if we repeatedly sampled from the target population using the same procedures that we used to create this single sample that we're looking at now. And what we can think about is we can think about the precision of the estimates of the beta coefficients that we have using the procedures that we used to create the sample, to create the data set that we have. And so precision is related to the amount of deviation that we see between repeated samples out of a population using a particular study design and what is true in the population. Now, what we're looking at here is we're looking at a study design which has very low precision. That's why we're seeing so much wobble here. And the low precision is primarily coming from the low sample size here. If you have a sample of only 10 individuals, that's a very small study. And one of the problems with that is that we have very low precision. Now let's change things. Let's see what happens to the precision if we increase the number of individuals that we have in each of our samples. So instead of sampling 10 individuals, what I'm going to do now is I'm going to sample 100 individuals each time. But in order for the computer to be able to handle this, I'm going to have to turn off drawing the red bars between the data points and the regression model each time. So we're just going to see the 100 blue data points and the regression model that is estimated, but we won't see the little red bars. So we start again with the structural part of the data generating process in the target population. This is what we're trying to estimate. And now what you can see, each of these samples has 100 individuals in it. And you can already see immediately that the amount of wobble in each of the estimates is considerably less than what we saw when we only had 10 people per sample. So what's happening here as we increase the sample size, we are increasing the precision of our estimates. And that means that from sample to sample, we are getting less wobble relative to what we are estimating underneath. So let's keep increasing the sample size and see what happens. So now from 100 individuals per sample, let's go to 1,000. We'll have a sample of 1,000 individuals. And so now you can see that the amount of wobble in the estimates from each regression model is quite small. And so here we can see the relationship between the sample size that we have and the precision of the estimates of the beta values in our model relative to the true data generating process in the target population. The bigger your sample size, the better the precision of your estimates that comes from your model. Because remember, your model is based upon a single sample, a single pink regression model estimated using least squares estimation if it's a linear outcome, and maximum likelihood estimation if it's a binary outcome. Okay, so we have talked about precision now. We know that precision is related to how much wobble we have in the estimates of the beta coefficients from sample to sample using our study design. So a study design that has more precision will have less wobble. One with less precision will have more wobble. One of the important ways that you can control precision is by the size of each of your samples. And usually what we're looking at is we're looking at a single sample. For example, that's what we're doing in our modeling exercise for this class is each of us has a sample from the NHANES. It's a sample of the US population. It's a quite large sample because we are starting with probably about 20,000 people in the sample because we're going across 4 different years of NHANES, combining them together. Each year they take about 5,000 people. And one of the reasons that we are combining 4 years is so that we can get greater precision in our estimates. So that's the motivation between putting together more than 1 year of NHANES data. Now, what I want to do is I want to move from precision to bias. And so what we want to do is we want to remember the equation that we used to generate the data in the target population, the structural part of the data generation process that we use. So the y values were equal to 2 plus 5 times x1 minus 5 times x2 plus the random component. So in our modeling process, what we're trying to do is we're trying to estimate the values of the beta coefficients, and especially we're interested in the beta coefficient for our exposure variable because that is going to give us the magnitude of the association between that variable, our exposure, and the outcome. And the other variables in our models are for conditioning so that we can control the confounding between our exposure variable and our outcome variable. So let's see what happens if we keep track of the values of beta 1 and beta 2 that are being estimated in each of these random samples that we're drawing from the target population. So what I'm going to do is now I'm going to run it again. I'm going to do a simulation, and the same that we did before. I'm starting with a target population of 2,500. I'm generating that target population using this equation, and then I'm drawing random samples of, let's use a sample size of 10. We'll have a lot of wobble in the model. And let's just keep track of the values for the beta coefficients in front of x1 and x2 that we're getting from each of these samples. And remember, those beta values are simply determined by the orientation of the model, and that is determined by least squares estimation. So let's just run this model, and you can see that as each of the samples comes by, we get an additional beta coefficient for x1 and for x2, and we're just creating a histogram that's keeping a record of the different values that we get. So what I'm going to do is I'm just going to let this run through 1,000 samples, and let's see how it looks after 1,000 samples. Okay, so this is just finishing up. Here's the count up here. It's at about 978, so it's almost finished. And so what we can see here is that after 1,000 samples, we can see the distribution of all of the estimates of beta 1 that we got from each of the 1,000 samples. And down here we can see the distribution of all the beta 2 estimates that we got from each of the samples. So each of these histograms contains 1,000 estimates of the beta 1 and beta 2. And remember, beta 1 goes with the value of x1. And in our original data generating process, the blue plane on this graph over here, the value of beta 1 was equal to 5, and the value of beta 2 was equal to minus 5. Remember, the equation was y equals 2 plus 5x1 minus 5x2 plus the random component. And so what we can see is that the method that we're using here, if we look at multiple samples, on average, this method that we're using, which is to use least squares estimation on random samples drawn from the population, and using the resulting model, the resulting orientation of the plane, those are the pink ones over here in our example, to determine the values of beta 1 and beta 2, that on average, it's actually giving us the true value of the beta 1 parameter in the underlying population. And remember, the underlying population here we created ourselves. I created that from the blue plane, and there's a structural component, which is the blue plane, plus the random component. And the actual beta 1 value was 5. It was y equals 2 plus 5x1. That 5 is the beta 1 value. And so you can see that our estimation procedure on average is giving us the right answer. And the same is true for the beta 2 estimate. The average estimate for beta 2 is minus 5. And what you can see here is we can already see that the estimates that we're getting are following a normal distribution. Now, it's still a little bit lumpy. We only have 1,000 samples here. But if we were to continue to take samples, we would see that this distribution would get more and more normal-like. And as we went to an infinite number of samples, this would become a perfectly normal distribution for both of these histograms. So this is a view from which we can see the meaning of unbiased. These are both unbiased estimates of beta 1 and beta 2 because on average, we are getting the actual value of the underlying parameter that we're trying to estimate. And what are we trying to estimate? We're trying to estimate that blue plane. We want to know what is the multiplier of x1 that causes the plane to have this particular orientation. And we know what it is because we said it. The value is equal to 5. And so here we have an unbiased estimate of that 5, which is the beta 1 value in the underlying population. And here we have the unbiased estimate, which is minus 5 for the beta 2 value, which is the multiplier for x2 that makes the blue plane have this particular orientation. Now, what would this have looked like if we had drawn samples of 1,000 data points instead of samples of 10 data points? Well, we already know that we would have had much less wobble in the regression models, and so the distribution of the beta estimates would have been in a narrower range around the values being estimated. So it would look like this. And so what we see here is that when we increase the sample size, the spread of the beta 1 and beta 2 estimates across multiple samples from the same study design have less variability. So this is another way to see that we have more precise estimates of the underlying value that we're trying to estimate. Now, in both of these examples, the one where we took samples of size 10 and where we took samples of size 1,000, in both of these examples, we had no bias at all. The modeling procedure, the estimation, was creating unbiased estimates of the underlying parameters. We know that because we know the beta 1 value is 5, the beta 2 value is minus 5. We set it up that way, and we can see that on average, the study design was creating unbiased estimates of those underlying parameters when we had a sample of 10 and when we had a sample of 1,000. So what would it look like if we had biased estimates? Let's look at an example where the estimate for beta 1 will be biased. And the way I'm going to do that is I'm going to introduce a little bit of error into the measurement of x1 values. So let's look at this. So here is the equation that I used to generate the data set that we've been using. And so the equation is y equals 2 plus 5x1 x1 minus 5x2 plus some error. So we created a data set that is determined by this function. And so what I'm going to do now is I'm going to create another variable. I'm going to call it x1 error. And the way I'm going to define x1 error is that I'm going to take the original value of x1 and I'm going to add another random error to it. So the original value of x1 plus a random error which has a mean of 0 and a normal distribution. And this is just to, oh, this actually should be error here. And this is just to create a variable that simulates what we have when we have measurement error. The true value of x1 is something, but what we see is a measure of x1 measured with error. So x1 error represents that kind of variable. And so what I'm going to do is I'm just going to run my regression model using x1 error. And so the model is going to be y equals beta 0 plus beta 1. And, you know, to us, it just looks like we're using x1. But since x1 is measured with error, this is actually x1 error. And then plus beta 2, x2, plus the error part. And so we're going to use the regression just like we've been doing to estimate these parameters. And we're going to be looking at the values of the parameters beta 1 and beta 2 that are estimated in each of the samples. So I'm just going to sample from this data set that has 3 variables, y, x2, and x1 error. And I'm going to estimate regression models like this, just like we've been doing with y, x1, and x2. Same thing, but now I'm just replacing x1 with a variable that's measured with some error. And let's see what happens when we do it that way. And so I'm using samples of 1,000 observations again, and we can see already that the beta 1 estimate is coming out around 3 instead of 5. And so what we can see here is that our estimate for beta 1 using our least squares estimation method is now biased. And it's biased because there is information error in our value of x1. So this demonstrates how information error in our variables that we measure can introduce information bias into our model. The true underlying beta 1 parameter here is 5. We set it up that way. But by introducing a little bit of error in the value of x1, we have introduced information bias into our model. Now these estimates are still very precise. So precision and bias are something different. You can have a not very precise estimate that is unbiased. That's what we had initially when we had an unbiased estimate using a sample size of 10. We had unbiased estimates, but the precision was low. Now what we have is we have high precision, but for beta 1 we actually have bias. So bias and precision are two different things. Now for beta 2, we still have high precision and it's also unbiased because we didn't put any information error into the values for x2. Okay, let's find the take-home messages in all of this. Let's think about what actually happens when we are doing research. So what I have here is, this is a picture of a sample. So let's say these are the data in your working data set, and you have values for your outcome, y, that's your effect, and your cause is going to be the x1 variable, that's your exposure variable, and you have one conditioning variable, x2. And so what you're going to do is you're going to ask your statistics program to estimate a model for these data using least squares estimation. And so your model is going to look like this, and it has the form y equals beta naught plus beta 1 x1 plus beta 2 x2 plus some error. And The beta 0, beta 1, and beta 2, these are going to be given to you by the statistics program, and they're basically just the values of betas that will depict the structural portion of your model, which is determined by the orientation of the plane. And that's determined by the value or the orientation of the plane that will minimize the square of the sum of the squares of the distances between each data point and the plane in the direction of the y-axis. But when we see these kinds of beta values, we need to think about their precision and whether or not, or to what degree, they are biased. And so to do that, we have to think about the underlying population, our target population. So you always have to have a population in mind. And here we are using the NHANES data. So our target population is the non-institutionalized US population. And so you have to think about, for these variables, X1, X2, and Y, your exposure and your outcome and your conditioning variables, there is a particular true structural component to the model of those data and the target population. And here our model, this is a mathematical projection we're making onto reality. We're saying that the data are actually generated through a process that has a structural component and a random component. And the structural component is the part that we're trying to estimate. Because if you remember back to the very beginning of the semester, we said that the model that we have, it's an abstraction for the patterns that we see in the data. And the patterns that we see in the data can be related back to our hypotheses about the causal structure of reality. So what we really want to know is, what's the causal structure of reality in the target population? But all we have is a sample. And one thing we have to remember is that the sample is drawn from the population, and it's not the entire population. And so the model that we see using the sample is not usually going to be the same as the structural component of the data generating process in the target population. But the amount of wobble that we would have in those regression models if we repeatedly sampled from the population using exactly the same procedures that we use for this particular sample could be quite different. If, for example, we're using a very small sample size, then if we continued to do that again and again and again with a very small sample size, we'd have a lot of wobble in the different models that we got from each of those samples. Whereas if we use a larger sample size, we would have much less wobble. And so we think about the precision, even though we can't see it directly. Now, what we're going to find out is that the statistics program can actually estimate the amount of wobble that is there. So for precision, we actually get some information from the statistics program about how precise our estimates actually are. Now, the other part of it is that our estimates may be biased. And what that means is that if we were to repeatedly sample, we were able to see the distribution of the beta values that we got by using this same study design again and again and again, on average, we would be estimating something. So the value that we are estimating on value, we say that is the value we're estimating. That's the, for example, for beta 1, if we did it again and again and again, the average beta 1 that we got, we say that's the beta 1 that we're estimating. Now, what we are estimating might or might not match the target population, and that's the meaning of bias. So, for example, we might have, if down here, the true beta 1 in the target population is right here where this arrow is, and we care about beta 1 because this is the parameter for our exposure variable, and we care about the association between this exposure variable, our cause variable, and our effect variable, which is the y variable. And that's what this beta 1 is going to give us. So this is the one we really care about the most. So, and what we want to know is the beta 1 here in the target population. So let's say this is it, for example. Now, if we had a study design that was estimating the true beta 1 in the target population, then we would have, on average, this is what we would be getting. But we might have a very precise study design, which means that all of the beta 1s that we get from all of the samples are pretty close to the truth, or we might have a less precise study design, which means that our beta 1 values are going to be spread out more distance from the true beta 1 value. So this would be an unbiased study design. This one in the middle is a precise one. This is a less precise one. Now, it's also possible that we have bias. And an example of bias might be if what we are estimating is over here, right? And so if we have a bias study, maybe this is the beta 1 value that we're estimating. It's not matching the true beta 1 value in the study population. That means we have bias. And we can have bias with a lot of precision, or we can have bias with less precision. So precision and bias are independent of each other. And the other thing is that bias doesn't always go in one particular direction. Bias can actually go in the other direction. So we could have bias that the beta 1 that we're estimating with our study design is up here. It's higher than the beta 1 value in the target population. And again, we can have a very precise estimate of that biased parameter, or we can have a less precise estimate. Now, the main thing that affects the precision of your study design is the sample size. Also, the amount of variability that's in the population naturally will have an effect on the precision. But the thing that we can control, and the thing that has a big effect, is the sample size. Now, one thing that you will hear people say is that they will say that the reason we want to have a larger sample size is because it reduces the bias in the study. Hopefully now you can see that that's not true. Increasing the sample size will give you a more precise estimate. It'll give you a spread of estimates with repeated samples that are closer to the thing you're estimating. But if you have a biased study design, like we see here in this example, if you have a biased study design and you increase the sample size, all you're going to do is get a more precise estimate of the wrong parameter. So you're going to get a very precise estimate of your biased parameter. So increasing the sample size does nothing to improve your bias. So when we think about the difference of the beta parameter that we see in our sample compared to the beta parameter that truly exists in the target population, we think about it as having error caused by two different components. One component is called random error, and the other component is called systematic error. If you have a lot of random error, then you have low precision. If you have a lot of systematic error, then you have bias. Low precision is caused primarily by your sample size. A small sample size will give you low precision. Bias has nothing to do with the sample size. Bias is caused by different things. There are different kinds of biases. The three major types of biases are confounding, information bias, and selection bias. Now, we will get some estimates of the precision in our study, the precision of our estimates from the statistics program, but for bias, we won't get these things. For bias, we have to use our wits. We have to think about our study design. For confounding, we've already spent a lot of time thinking about confounding. That's the purpose of the directed acyclic graphs. So we can actually control for confounding, at least partially, using the structure of our model by conditioning on variables that we need to condition to block backdoor paths. And we can think about information bias and selection bias. Now, there are methods that we can use to minimize information bias and selection bias in our models, but they're beyond the scope of this course. And so what we're going to be doing is we're just going to be thinking about information bias and possibly selection bias if we have time, as part of thinking about the uncertainty in our modeling results. So the main thing to remember now, though, is that when we're talking about precision, we're talking about how spread out the estimates of the beta values are in repeated samples. And for bias, we're talking about the parameter that's actually being estimated. Does it differ from the true parameter in the target population? So that hopefully will give you a better understanding of the meanings of bias and precision.